In another video, we learned how to define the normal distribution, and we attempted to be more comfortable with the total area underneath, as well as how does the normal distribution change when sigma is a different magnitude. In this video, we'll learn how to calculate z-scores, and we'll learn how to determine the cumulative proportion using the z-table, or table A. So just recall that a normal distribution has this, well, not quite this, has this bell-like shape, okay, with one peak and two tails. Mu is the population mean, and it designates where that peak occurs. And then standard deviation, or the average difference between all data points and the mu, happens at the inflection point, where our inflection point is some point x, and our standard deviation is the distance between that point and mu. So there are many different normal distributions, and that's because mu can be any real number and sigma can be any non-negative. Well, actually, we probably want it to be positive. It could be any positive real number. And so what we want to do is we want to standardize each distribution in order to be in the same scale. So that's really the motivation for how to do it. So the reason we want to do it is so that we can compare values on one normal distribution to another. So the idea is to take this normal distribution here, which is defined by mu and sigma, and we want to turn it into something called the standard normal distribution. And the standard normal distribution has a mu 0 and a sigma equal to 1. And how do we do this standardization process? Well, we do it by calculating z-scores. And so we calculate that by setting z, which is just a variable. You can call it whatever you want. It just so happens in statistical literature we use the letter z. Z is equal to x, your value on your normal distribution defined by mu and sigma, minus mu over sigma. Okay, so again, just a reminder that mu is the population mean and sigma is the population standard deviation, and x is the value that we care about on the normal distribution with mean mu and standard deviation sigma. Alright, so why is the z-score important? Well, the z-score, and I'm just going to continue the details here. The z-score tells us how many standard deviations the x is away from mu and the direction. So we get this just by rewriting the z-score formula and solving for x. So moving sigma to both sides and then adding mu to both sides, we get x is equal to mu plus sigma times z. So z is how many standard deviations x is away from mu. And a way you can understand this graphically is, let's just draw some standard deviation with a generic mu and some value that we care about x. When we use the standardization process, what happens is that we go to this standard, or this normal distribution with mu 0, and this x is then going to be z. So it's the same distance as x is from mu, And so we're preserving distance. We're just changing the scale, okay? And so we can also think of it like this, where x is on the other side, and when we standardize, what we'll get is, here's the distribution, 0, and then the z over here is going to be the same distance away from 0 as x is from mu. Alright, so just recall the data set on resting pulse rate for 9 different patients at some hospital, and remember that we are able to create a density curve or find a density curve which generalizes that histogram that we saw, and we want to find a z-score. So let's say that for that data, let's say mu was equal to 92, and let's say sigma is equal to 14, okay? So if we want to find the z-score for someone who has a resting pulse rate 95 beats per minute, then we just want to use the formula from earlier. So plug in 95 for x, okay, minus 92 for mu, over 14 for sigma, and that's equal to 3 over 14, which is equal to 0.2142. Okay, so again, this is the same as the formula x minus mu over sigma, where x is coming from the data that's given. It's telling us we care about 95 beats per minute. Mu, I gave this to you, this mu and sigma, which will often be the case in problems involving the normal distribution. Now, because total area is 1, so let's just write that down as a reminder, total area under a density curve is equal to 1. This implies that some proportion of the area, or some proportion of the area under the curve represents a percentage of the population, okay? So proportion, and proportion, by this I mean any number between 0 and 1. Proportion will represent the percent of the population, okay, or a fraction of the area under the density curve, or fraction of area under curve. Alright, so for the area from x to the left, this is called the cumulative proportion. So let's say this is my normal curve, let's say this is my mu, this is my standard deviation. Let's say that this is my x value that I care about. So what we're saying when we're talking about cumulative proportion is that the area from x to the left is my cumulative proportion, okay? And you can think of this as, in terms of the word cumulative, so remember when we're talking about a cumulative exam, it covers all material up to that point. Okay, that's the same idea here. Cumulative proportion is the area under the curve up until x. Okay, so cumulative proportions are the area from x to the left. And left is key. So cumulative proportions and z-scores are intimately related in this class with something called Table A. Okay, so Table A, if you went to Google and you typed in a search for z-score table, it'll pop up. For the textbook that we're using, which is the
Basic Practice of Statistics, 8th edition. Table A is in the back of your textbook. And so I just want to show you what this looks like, okay? Here you can see that we have, it's labeled Table A, standard normal cumulative proportions, okay? So this is how Table A is related to the cumulative proportion. In the topmost row, in the leftmost column, it's defined by the z-score, okay? So now this is how Table A is related to the z-score. And we use our z-score, or where the z is located on the x-axis of the standard normal curve, to find our cumulative proportion. Okay, and so it's nice that table A has this figure for us. Okay, so here's the standard normal curve where this center would be 0, and here's our z-score, and then here's the cumulative proportion. So what we can do is find the z-score, and then we can use this table to find the area to the left. Okay, or if you're given the area to the left, you can find your z-score. Okay, it works both ways. All right, so we're just going to document these steps
of how we can use table A. So, step 1, use the leftmost column and the topmost row to find a close approximation of the z-score. Okay, and then step 2, once we've found that close approximation of the z-score, find where the leftmost column and the topmost row, I'm just going to highlight this, find where the leftmost column and the topmost row intersect. So find where these things intersect. Alright, and where these intersect, this becomes the cumulative proportion. Alright, so recall that we have the z-score already for x equal 95. Okay, so x is equal to 95. We found in an earlier example that z is equal to 0.2142. Alright, and what we want to do, and just pay attention to keywords, okay? So here at most 95 tells us that here's our distribution. We said that mu is equal to 92 and standard deviation is 14. And we care about 95 as a value, so this is 3 away, so it's like 95 is right here. Okay, and at most 95 says that we care about the area to the left. Okay, so at most means all beats per minute except up to 95. Alright, so now let's go to table A and we'll find the 0.2142. Alright, so to our textbook.
0, 2. So notice these are negatives and our z-score is positive. So we want to continue sifting through the table until we get to the positive values. Still negative, still negative, still negative. 0 is both negative and positive according to this table. I don't know why my mistake is so long. Alright, so we're trying to find 0.21 something. So 0.2.01. So we're sort of putting these numbers together. So really what this z-score reads is 0.21. Okay? Think about adding them together. Alright, so we have 0.2142 as our z-score, and if we rounded, it would be 0.21. So that tells us that our cumulative proportion is 0.5832.
Okay, so this area here is 0.5832. Notice it's a fraction of 1. Okay? And you could also give a percentage, 58.32, but please pay attention to what the problem is asking for. This says proportion, give the decimal version, and if it's talking about percentage, please give the percentage version. If we said at least, then that is implying that we care about the area to the right, because at least 95 BP means 95 or 96 or 97 or any number from 95 up. Okay, and the way that we find at least is 1 minus what's to the left. 1 minus 0.5832 and that's equal to 0.4168. So keywords are very important here.